Okay. All right, so chapter 3 is all about vectors. So as I just said, we're going to start off with that what is a vector kind of ideas, and we're going to go from there. After that, we'll do a little bit of application. Like I said, we're not going to do as much as we normally would in this semester. And we're getting into the algebra of vectors. That's that vector operations, add, subtract, multiply, all that kind of stuff. But that last piece is how we multiply different vectors to each other, and there's going to actually be 2 sections on that. So these first 2 ideas are really our 12.1, and this last idea is really the 12.3 and 12.4 piece of this. So we're going to start off with what are vectors.
I'm applying for a new film loan. Go by the name of Vector. That's a mathematical term. Quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Alright, so that is what vectors are. It's an object with both a magnitude and a direction. So I was deciding whether I should play that video or act that out. I decided to play with it. Probably safer that way, right? Alright, but that's really the idea here. What are vectors? One of the interpretations of vectors, it is an object with both direction and magnitude. It's represented by an arrow, at least in 2-dimensional space. That's kind of our base representation. So here I have a vector drawn. I have an arrow in 2 space. It has a direction. It's pointing that way. And it has a specific length. It's going from P to Q. And so how do I mathematically represent this thing? And one way to think about this representation of vectors is that it is the directions. The directions from P to Q. So if I was standing at P, how would I get to Q? That would be described by this vector. And if I was standing at P and I wanted to get to Q, well, I'd travel in the x direction 1, 2, 3, 4. About a distance of 4. And I'd go up 1, 2. 2. And so one way I can represent this vector, PQ, with a little arrow, that's why I'd represent the vector from P to Q, would be with 4 in the x direction and 2 in the y direction. That's one way I can write vectors, with these little arrows on either side. I can also write them in what's called ij notation. So I can say 4i plus 2j, where I and j are essentially the axis directions. Oops, flip that. I is over here, j is over here. So I is like the x direction, j is like the y direction. Actually, what we're going to find out is that these pieces are called unit vectors that point in these directions. We'll kind of define what that is later. These are different ways we can just write out vectors. In fact, there's lots of other ways we can represent vectors. In different applications, you might see them as column vectors, where they just write them vertically and they make them look like this. You'll see them look like this a lot of times in linear algebra. All just different ways to write vectors. Yep?
So, with it just being different ways, does it matter how we write it on the exam? Because, like, I know the first one I took Calc 2, my instructor made it very clear that he wanted it to be like, is it like I hat, J hat, A hat, or an arrow over the I and J?
I have no preference. In class, I'm going to almost always write them like this, because it's the shortest notation, the least writing possible. Okay. Right? I don't care which way you do it. I will say that this is really kind of a linear algebra notation, and your book will use either this or this. Now your online homework will also have a specific way they want you to enter it typically, but they should state that as you go into those problems. In our old homework, they really wanted that IJ notation, which is probably why your instructor really emphasized it. I believe this online homework system uses more of this notation, and they'll even enter in the values here for the components. As far as an exam goes, write it however you want as long as it's correct. Okay? So in other words, this would not be correct. Right, we're kind of blending the notation here. So you can pick whichever one you want, but use it correctly and use it consistently. Okay. Okay, so I have my vector here. This is the vector 4, 2. If I go over 4, I go up 2. This is called a displacement vector. It describes the displacement from P to Q. But this isn't the only vector for 2, because the definition of vector says I need a direction and I need a magnitude. But it doesn't say anything about starting position. So if I talk about a vector that's over here, and if I were to go over 4, 1, 2, 3, 4, up 2, like this, that vector has the same magnitude, it's got the same length to it. I use for the name of length. And it points the same direction. It points that way. So these two vectors are the same. They are identical. They are equal to each other. I'll call this vector u. Once again, with that little vector symbol, sometimes we use one letter to represent them if we don't have specific points. But u is equal to the vector pq because they have the same direction and the same magnitude. So with all these different vectors kind of floating around like this that are all the same, I could draw a whole, infinitely many more of these that are equal. It makes it kind of confusing to work with them. So what we do is we talk about position vectors. So we talk about this being a displacement vector. A position vector is just a vector whose tail starts at the origin. So we have a tail, which is where we're starting from, and we have a head, where we're ending at. And so a position vector is just a vector that starts at the origin. In this case, we'd go over 4, up 2. This would be the position vector. And while we can have infinitely many displacement vectors that are equal to 4, 2, we can only have one position vector that's equal to 4, 2. It's this one. Starts at the origin, goes over 4, up 2. So that position vector is unique. While in general we talk about the vector 4, 2 not being unique. Any questions about the difference between position vectors and displacement vectors? Okay, now oftentimes we want to calculate a displacement vector. When we calculate a displacement vector, it's kind of like we're finding out which position vector is equal to. I have two random points up here. When I calculate this vector, I say I go over 4, up 2, I'm getting this representation, this 4, 2, right? Which is really kind of describing which position vector I'm working with. If I talk about this position vector, it's the one at the point 4, 2. So how do I get this thing? I mean, it was kind of easy in our case. I said, well, I'm going over 4, I'm going up 2. But in general, how would we calculate that displacement vector? We would want to find the change in the x. This is really the change in the x. It's really taking my final x value minus my initial x value. And the same thing for the displacement of the y value. It's going to take a final y value and subtract off my initial y value. So if we think of these 2 points here, P is at the point -3, 2. And Q is at the point 1, 4. So what is PQ? Well, it has a final x value of 1. It has an initial x value of -3, so I subtract those two values. My final x minus my initial x, and I take my final y, which is 4, minus my initial y, which is 2. When I do those calculations, I get 4, 2, which of course is the vector. So that's one way to think about it, is taking the final x minus the initial x, the final y, the initial y. But as we get to the next step of learning about what vector subtraction is, this is kind of going to look like that final point minus that initial point. It looks like that. Right? Don't tell other mathematicians I'm writing this. We really don't subtract points. But it feels like that. It feels like I'm going 1, 4 minus -3, 2, and just subtracting their little bits here. That's kind of what we're doing. But the order is important. It says final minus initial. Any questions so far? Okay, as you prep for today, hopefully you read through 12.1. You saw there's all kinds of vector operations. They're relatively straightforward. Right? Once we learn how to do them, they're not too bad to apply. So we're going to go through them real quick. A bunch of vector operations. So I have two vectors here. I have the vector v, this is v, and the vector pq, and I give you the points pq. And I want to calculate all this stuff, and then I also want to see what it means, see what it looks like. So we'll start off with the first piece. I'm going to let the vector u just be a different name to the vector pq. Kind of name them whatever I want. But what is this vector? Go ahead and calculate this displacement vector. What is the vector pq? So I'm going from P to Q. I will take my final x value, that's negative 3, minus my initial x value, and that's the wrong point here, isn't it? This should be negative 1. Sorry about that. Yep. So minus my initial one. And then I have my final y value minus my initial y value. Negative 3 minus negative 1 is negative 2. And negative 1 minus a negative 4 is positive 3. So I have my result here, and it should make sense. This says go negative 2 in the x direction, go 3 in the y direction. Sure enough, I'm going back 2, up 3. So it makes sense. It does describe that vector. And of course, that tells me also the associated position vector. The associated position vector would be back 2, up 3. It would be this vector. That would be my associated position vector. Now the next piece is 2 times u. I'm taking my vector and I'm multiplying it by a number. And to do that, all I do is multiply each of the components by numbers. Here's my vector, here are my components. This is the x component, this is the y component, and sometimes I write their components like that. And so 2 times my vector, negative 2, 3, is just negative 4, 6. I just multiply each of the pieces by 2. And the result will be a new vector. Here's my vector, negative 4, 6. And now I want to see what this looks like as a position vector. As a position vector, let's go negative 4 and up 6. Right about here. So my vector would look like this. Huh. What does that tell me about multiplying vectors by numbers? What am I doing when I'm multiplying this by 2? I'm just scaling it. I'm not changing its direction, I'm just scaling it. In fact, when I multiply by 2, I am doubling the length. That's what I'm doing here. So if I wanted to think about what 3u would be, well, it would just be this thing. 4u would be all the way out to here, once again from the origin, but those would be 3u and 4u as vectors. What would negative u look like? Yep, this would be negative u. Opposite direction, same length. Negative 2u would look like this. So when I multiply vectors by numbers, I'm just stretching them. I'm scaling them. Any questions about that? Alright, u plus v. When I add vectors, I am just adding their components. So if u is negative 2 and positive 3, and v is, let's see what v is, it's 4, 2. When I add vectors, I just add their components. So I add their x pieces together, negative 2 plus 4, that's positive 2, and 3 plus 2 is 5. And then once again, I want to plot that and see what that looks like. I go over 2, I go up 5, puts me right about here. You may say, well, what does that look like graphically? Well, if I could draw this perfectly, it'd be a little bit clearer. But when I add two vectors together, what I get is the diagonal of a parallelogram that's made by the other two vectors. So in other words, I have this vector as one side, this vector as another. If I made a parallelogram, and there everything was drawn perfectly, it would look like this. And the sum of those two vectors would be the diagonal of that parallelogram. That's one way to visually talk about the addition of vectors. Another way that I can add vectors kind of graphically is by putting them tip to tail. It says first go over -2 and then up 3 and then do this thing. And then go 4 and 2. So graphically I'm putting them together just by following the directions. It's going to look like first going -2, 3, that's doing that first vector, and then doing the second vector. So I can think of vector addition as the end point when I put them tip to tail. First I follow this vector, then I follow the other vector. This is where I end up. That vector is the sum. Any questions about that? So this vector right here is the vector that is u plus v. All right, then we do subtraction. Go ahead and subtract those two vectors. In addition, we just added their components. Subtraction, we're just subtracting their components. So what do I get here? What's u minus v? -6 of 1. Absolutely. I just subtract their x values, subtract their y values in the appropriate order. I get -6, 1. What does that thing look like? Let's see, -6, 1 looks like 1, 2, 3, 4, 5, 6, and up 1. It looks like this vector. Not really sure what that thing looks like until I pick it up and I move it right here. And that's the visual representation of subtraction of two vectors. If I take u and I subtract v, visually that's going to give me a vector that points from v to u. Okay, so u minus v points from v to u. And that kind of makes sense because if I talk about this vector v, I talk about 4, 2. But if I said what point is this, you'd say that's the point 4, 2. Position vector and the point are almost indistinguishable. We really think of them almost as the same. And so if I wanted to find the displacement vector that went between these two things, I would take the final point minus the initial point. Or really, the final vector minus the initial vector. U minus v gives me the vector that points from v to u. Okay? All right, any questions about subtraction? All right, the calculation is very easy. You also want to make sure you're happy with this visualization because you will be required to sketch these things. I will say, what does subtraction mean visually? Sketch out this vector. Sketch that out. All right, the next one is this weird symbol. This says the magnitude of u. It's the length of u, sometimes called the norm of u. All kinds of different names for this thing. How long is the vector u? Well, if we're thinking about this vector in terms of position vectors, we can always calculate this thing. So here is u. Let me clean this up just a little bit. Here's my vector u. This was -2, 3. If I want to find that length, I could always do it using Pythag. If it's a position vector, I should be able to drop a perpendicular and make this little mini triangle. If this is my little mini triangle, I need this squared plus this squared equals the hypotenuse squared. But what is this value? -2 is just my x component. So if I know this is the vector -2, 4, I know this length is -2. I know this length is 4. Because those are just the components. So that means my length should be the square root of the x component squared plus the y component squared, just through that Pythag representation. So in this case, I have the square root of -2 squared plus 3 squared. The square root of 4 plus 9, the square root of 13. And that should tell me how long this vector is. Any questions about that? All right, the next one is the unit vector. This little vector U with a hat symbol instead of an arrow on top of it means it's the unit vector. It's the unit vector in the U direction. So the idea here is that sometimes I only care about the direction of the vector. I don't care about how long it is. But when I use that vector, when I play with it, it has some sort of length already built into it. So I wish I could remove that component of it. Just keep the direction, but not have some weird length that's messing up all my calculations. And that's what the unit vector does. The unit vector is a vector that points in the direction of u, but has a length of 1. So it points in this direction, but it has a length of 1. So how do we get this thing? Well, I know the direction of u. U has the direction of u. The only problem is that u has some sort of length associated with it. But now I know how to change its length. If I multiplied it by 2, I would double its length. So let's pretend that u has a length of the square root of 13. If I were to multiply u by something to turn it into a length of 1, what do I have to multiply it by? What? 1 over the square root of 13. So for this one, to find a unit vector, it would be 1 over the square root of 13 times the vector u, which was -2, 3. And I could write it like that, or I could actually do the multiplication and get -2 over the root 13, 3 over the root 13, like that. It has to point in the same direction as u, because all I did was multiply it by a number. That doesn't change the direction. And if I actually calculated the magnitude here, it would have a value of 1. So that's how we did it for this one specifically, but in general, it's easy enough to get a formula for this. We just take the vector and we divide by its length. You know, divide by or multiply 1 over the length, whichever. So this would be a formula for the unit vector. So these things will all be on the exam. I will give you 2 vectors and say, yeah, do all this stuff. And all the calculations are relatively straightforward, so you should be able to zip through this. This is something that would probably be on the non-calculator portion of the exam. Any questions about these calculations? All right. Your turn. Here's a couple of vectors. You can assume that they're integer valued vectors here. So I just kind of sketched them out. You can assume I didn't try to draw it to be 2.985. Go ahead and run these calculations. For tomorrow, I'm going to assign you to watch one of the videos on MathVids. There's also an Introduction to Vectors video that pretty much covers all this stuff. I really meant to assign it to you before today, so I didn't have to talk through all this. I forgot to, so that's kind of why we're going through really from the basics from step 1. For some of you, this is really easy. You've seen it a bunch of times before. But there are definitely some of you in here who have probably never seen vectors, and I want to make sure we're not going too quickly over the core ideas. Not a quiz also, so you can compare your answer to your next question. Check. edge over here. I'll call it minus 2. So v is at minus 2, negative 3. Wanting an integer value, so didn't call that very good. Alright, so I went through most of my calculations so far, kind of the real basic ones. So I have the vector 1, 3 over 1 of 3. I have the vector I calculated using the subtraction here. My final x value minus my initial x value, final y value minus my initial one. I got negative 4, negative 1. That makes sense. Please, please, please look at your vectors when you're done. This should go to the left 4 and down 1. Sure enough, it goes to the left 4 and down 1. Okay. So what I decided to do after that was just kind of put this in place as its position vector. Negative 4, negative 1 would also look like this. These two vectors are equal. Then I look at the sum of the two vectors. I'm just adding their components. If I'm just taking 1 plus negative 4 to get negative 3, 3 plus negative 1 to get 2. Now once again I want to say, does that make sense? Well, this vector, negative 3, 2, would look like negative 3 plus 2. That vector. And that does kind of match my parallelogram idea, certainly in the ballpark. And my scale is obviously a little out of whack here, but you can imagine it being in the middle. Then I have the difference between the two vectors as negative 5, negative 4. So this is AB minus V. This should be a vector that points from where to where? From which vector to which vector? So is it going this way or is it going this way? From V to AB or AB to V? Well, the nice thing is if we forget, we just do the calculations. Right? It's easy enough to subtract the components and we get this value. Negative 5, negative 4. Negative 5, negative 4 means I'm going from V to AB. Negative 5, negative 4. Okay, So it's a good way to remind yourself. You can also think about it as final minus initial. That should be my -5, -4 value. And then 2 times v, I just multiply the components of v to get 2, 6. And of course, you could plot that to see a scaling of the vector v. Any questions about those ones? Now, that last one's a little bit trickier. Find a vector that points in the direction of v but has a length of 10. How do I do this one? Yep. Absolutely. The reason I like that unit vector is because it has a nice known length. I don't know, the vector v might have a length of square root of 3. I can't really multiply that thing by 10, so I can go through the unit vector first. First I'll turn it into a unit vector which has a length of 1. Then if I want it to have a length of 10, I just take 10 times that unit vector. So that's why one of the reasons unit vector is so important. So this thing is really just going to be 10 times the unit vector. 10 times the vector v divided by its magnitude. So what is the magnitude of v? Well, it's the vector 1, 3. So this should be the square root of 1 squared plus 3 squared. Looks like it's the square root of 10. So what is this vector here? This vector is 10 over the square root of 10 times the vector 1, 3. And once again, I could really leave it written like that. That's fine. You want to multiply it through to say this? You're more than welcome to. Absolutely not required, though. And this is college, not high school, so you absolutely can leave that radical in the denominator, and that's just fine. Any questions about this? Okay, so when I started off, I talked about the representations of a vector. And I said it's something with magnitude and direction. And it can be represented by an arrow in 2 dimensions. But that's not the only representation we have for vectors. In fact, we can think of vectors much more generally. And that's very useful. So here's 2 other ways we can think about vectors. We can think about them as an ordered list of numbers. I just look at the vectors. I looked at the vector 1, 2. Now for those of you who have worked in 3 space before, 3 space being the real world here, x, y, z, not just x and y, that should also have vectors. I should be able to draw an arrow that goes from the corner of this desk up to here and describe that change. But that change is going to be a change in the x, a change in the y, and a change in the z. So I expect that to have 3 components. I expect that vector to look like the vector 1, 2, 3, or 4, 6, 8, a list of 3 values. But what about if the world had 4 dimensions or 5 dimensions? I don't know what that looks like. I can't draw that with an arrow, but there's no reason I can't just make a longer list of numbers and call that a vector. And so the whole magic here about vectors is that I can think of this as a vector. 1, 2, 3, 4, 5, 6. Whatever. That's a vector in 6 space. I don't know what that looks like, but I can write it. I could write another vector in 6 space, and I could add them, and I subtract them. I can find out how long this vector is, because I can add those ideas of calculation that I've already used before. So the magic of vectors is I can do this thing in 2 dimensions, where I have physical relationships. I can see, yes, this vector is so long. But the calculation of that just required these numbers. And so this will let me extend these ideas to higher dimensions, to word problems where 6 dimensions make sense, for instance. So one of the magics of vectors is I had this nice 2-dimensional physical representation, but I have a way to generalize it to higher dimensions or to other settings. I can also think of vectors as an element of a vector space. This is a linear algebra idea. What a vector is in general. It says, does this stuff have to be just arrows? Does it have to be just numbers? Could I think of functions as vectors? As these things that I know how to add, subtract, multiply, and work with in vector spaces. That's something else you can do. So we can take the same basics idea, all the stuff we are going to learn about in this class, which is just the 2-dimensional representation, and think of all those ideas we use. You'll be able to extend those to functions, to matrices, to 6-dimensional space, all kinds of things. That's really the power of vectors underneath. Any questions about that? All right. Parallel and perpendicular, we're just going to focus on parallel for now. Are U and V parallel? Is there a way I can determine if vectors are parallel or not? So first of all, we look at them. Are U and V parallel? They look parallel? They look parallel. I try to draw them parallel. What makes them parallel? Why did you think they were parallel?
Same slope.
Absolutely, same slope. What is slope? It's just the rise over the run. It's the change in y over the change of x. So as I change my x value, I will change by an associated value of y. If you give me an x and a y and those proportions are the same, you're essentially giving me the same vector because the vector tells me the relationship between the x and the y. In fact, not only are these two vectors parallel, but if I thought about what they look like, this one looks to be like the vector 1, 3. And here, if I calculated the displacement vector, if I just said I'm going over 1 and up, well, 3, this one also looks like 1, 3. In fact, these two vectors are equal. What if this vector was like that? Longer. It wouldn't be 1, 3 anymore. Now it would be something like 2, 6 maybe if I doubled it. Would they still be parallel? They would still be parallel. Because even though they're scaled differently, they're basically the same vector in disguise. Remember, if I'm talking about displacement vectors, I can take this thing and move it wherever I want, starting whenever. And really its description as a position vector is the unique thing. So if I look at any different parallel vector over there or over here, when I actually write them out in vector form, when I write out what that vector is, as a position vector, it should still be just a scaling of my original vector. They should really be pointing in the same direction. So given two vectors, how can I tell if they're parallel? If U is parallel to V, if U is equal to C times V for some scalar C. If the vectors are just multiples of each other, then they're parallel. That's kind of what that visualization was showing. So as is usual with this section, kind of like once you know the answer, there's really not much to compute. I would say, is 1, 2 parallel? That's my symbol for parallel, and I'll put a question mark here. Is it parallel to 1/2, 1? Yep, they're just multiples. Is it parallel to -2, -4? Just multiples. That's all we're doing. We're just testing to see if there's multiples or not. All right, any questions so far? All right, we've done quite a bit so far. We know what vectors are, we know how to represent them, find displacement vectors, how to add them, subtract them, tell if they're multiples, tell if they're parallel. We've seen that we can compute all kinds of stuff now. Sort of. I mean, we can compute it when you give me the vector is 2, 3. And I can add that to the vector that is -1, 4. But when we started, we just said a vector was something with magnitude and direction. So if I have a map, and here's Houghton, and I want to fly to Marquette, I want to fly there, I'm not going to say, well, how do you get there? Well, you go down this far and you go over this far. No, I'd want to say you want to go this way. Now I want to be able to describe that in words. So I wouldn't say you go south this far and then you go east this far. I'd be more likely to use a distance to travel and a direction to travel. Go 30 degrees southeast and fly for 90 miles. And that's a useful way to describe a vector. That's a useful way to talk about an application and describe the vector. But that's not a very useful way to calculate with vectors. If I said, here's a vector, it has a length of 4, and it's 30 degrees above the x-axis, and I want you to add that to this other vector that has a length of 2 and is 20 degrees below the x-axis. I don't know how to add those things. Maybe I could do it with enough time and some geometry and some weird stuff, but it's certainly a lot harder than just adding 2 comma 4 to 3 comma 6. So the idea is when we get this physical representation for a vector, we want to turn it into that nice component form. So that's this step. How can I take that description and get just the nice component representation? Well, here's what I know. I know this vector has an angle 30 degrees. That's kind of 30 degrees. And it has a length of 4. So this length is 4. I'll call this vector, the vector's called u. But what I want to get is this thing. I want to get the x component and the y component. But just like when I calculated the length of a vector, as long as we're talking about position vectors, I can really generate a right triangle just by dropping a perpendicular to the axis. That's very useful because what is the x component? It's just this length. And what is the y component? It's just this length, which now are just 2 legs of a right triangle. Which means I get to use some trig. Yes! You guys learned it a while ago and you're like, I've been waiting to use my trig for so long. What's the trig relationship that's going to help me find out the x component? What's the trig? Cosine. Cosine tells me the opposite over the hypotenuse. So I know that cosine of 30 degrees should be equal to this piece, the side adjacent, over the hypotenuse. So that means the x component is just 4 times the cosine of 30 degrees. Or more generally, 4 is just the length of the vector, and I'm just taking the cosine of that angle. Now what about the y component? What's that expression going to be? What's that formula going to be? Absolutely, just the magnitude of u times the sine of theta. So now we have 4 cosine of 30 degrees, 4 sine of 30 degrees. Somebody chug that out on a calculator for me. Everybody chug that out on a calculator if you have a calculator. Everybody who has a calculator to calculate this value for me. Oh, 3 squared plus 4 squared. I think that'd be a hypotenuse of 5. We need that to work out. So we need 3 squared plus 4 squared would equal 5 squared. So 5 would have to be the hypotenuse there. And it turns out this will definitely not be that value. Because if you think about it, this is going to be Smaller than 1, bigger than 1, or equal to 1? I'd be smaller than 1, which means this guy's going to be smaller than 4. I guess that doesn't really tell me much about the length, but anyway. All right, so what is this value? Somebody give me the x component.
3.46.
What was that over here?
3.46.
3.46. What was this over here?
That's wrong.
What was it though?
It was negative 3.96.
Negative 3.96. Okay. Yep. And this is why I had everybody do it. Because what's probably the problem here? Radians or degrees, that's going to be the problem. So I would guess there's probably quite a few people like, oh yeah, I'm in radian mode because they always told me in calculus, don't ever put it in degree mode. Until you get to vectors and you're doing 30 degrees, right? You could certainly do this as pi over 6. That would be fine. That would be radians mode. But you have to be careful about what mode you're working in. Yep. Y component, anybody? 2? Yep, that makes sense. All right, so those look like good values. Now, once again, if you had it in the wrong mode, odds are pretty good that you should notice that when you look at the actual values. If you're getting a negative value here, you got to say, oh, something's going on here, right? I don't expect to get a negative value. Now, it could work out, just coincidentally, those values could be close to each other. They could be maybe right. Right, so you just got to be careful. Just be careful if you're working in radians or degree modes. Okay. All right, any questions on this? All right, what if I was over here? This one has a length of 6, and this angle is 70 degrees right there. This is my vector W. First, I want the formula here. I'll drop my little perpendicular. I got my right triangle. What's going to be my x component here? Six cosine of 70, 6 sine of 70. Plug that into your calculators. I get an x value of what?
2.05.
2.05. I get a y value of 5.64. That can't be right. What's wrong here? Something's wrong. Does that vector look like 2.5? It's got to be a negative, right? There's a couple ways you can do that. A couple ways you can think about this. This theta in the formula is not this theta, it's this theta. And so if I did calculate 90 and another 20, it'd be 110. I did cosine of 110, that should work out. You don't have to do it that way. You certainly can use the 70, but then you have to adjust for the sine. You have to know that when I do the trig, I'm getting this magnitude and this magnitude. And when I get this to be 205, I know that's negative because I'm over here, because the picture tells me that. Okay. So just be aware of that. You can either use the acute angle and adjust the sine manually, or you can use the full angle. And it should account for that. What is the cosine? What is 6 times the cosine of 110? Negative 2.05. Okay, so that will work. All right, so be careful with that. Any questions about that? And once again, why? Why do we do this? Because I did not know how to add U and W before. But now I can. Now it's easy. Now I just add their components and I'm done. Okay, so it's much easier to work with, to do algebra-ish stuff on vectors if they're in component form. So a lot of times we'll take the physical representation, turn it into components, and then do stuff like this with it. Here's some vectors. Here's A, B. I know that A plus C equals B. What's C? What is C? 2, -1. -1, sorry. I said it, didn't write it. How'd you get that? What did you do? Absolutely. So you had C equals B minus A, like that, right? What gave you the right to do that? That would be my question, right? We don't know if we can do that. We know we can do that if these are numbers, but can we do that with vectors? That's a pretty big assumption. And so it's a good assumption, but we have to understand that there is an assumption here. These are vectors. You have never worked with vectors potentially before. You certainly can't assume things about real numbers and generalize them to vectors. If I was working on a regular algebra problem, this thing, you would just subtract 2 from both sides. But that's really not what you're doing. You're saying that this is the same as -2 plus 2 plus x equals -2 plus 5. And I can add that value to both sides. But to choose that value of -2, you need to know that there was some magical 2. You need to know that there existed for every real number an additive inverse, this thing called -2, that if I add these two things together, what do I get? 0. And you wanted to get to 0 because you know that there is a 0, and 0 plus x is just x. So you knew all these rules. Now actually, when we did this first operation, first we had this thing, and now we added the -2. But you want to add the -2 to the 2, so you want to actually do this thing. Can you do that? Well, sure you can with numbers. We have a property that tells us we can do that. What is that property called? Anybody know that property? It's the associative property. That's the associative property of real numbers that tells us we can do that. Okay, we have all these properties for real numbers that let us do algebra. The question is, do we have all these properties for vectors? Can we do algebra with vectors? And yeah, we can. So I think I got them all in there. So these are the properties. These are all the properties. This book gives us a big list of them. It says we have the community property for vector addition. We have the associative property for vector addition. All this kind of stuff. So we have this giant list. And if you just look at it, it's like, oh, goodness, that looks kind of big and scary. But it's really just telling us you can do all the algebra stuff you really know with real numbers. Yeah, you can do it with vectors too. So when you want to subtract v from both sides, you can go ahead and do it. And that's basically what this is telling us we can do. But it's good to think back to that core concepts to really understand the structure that we're using here. So we have the commutative property, the associative property, not just for vector addition, but also for scalar multiplication. This is called alpha. It's just a Greek letter. This is beta. So it doesn't really matter which order I multiply in. It's the associative property of scalar multiplication. I have the rest of my distributive properties. I have these weird identity properties. If I multiply a vector by the number 1, I get the vector. And we all kind of assume that, but this just tells us, yeah, it's all true. Yep.
Are we going to need to know the names of them?
I'm not going to test you on the names for them. You will not have to know them for this course, but you see them kind of everywhere. You've learned them probably a whole bunch of times throughout high school. You've seen them again now. If you take linear algebra, you'll see them again there. If you take any kind of abstract mathematics, you'll see them again there. So, you know, it's just good to have them kind of in the back of your mind. Now, I'm also not going to make you prove these on the exam, but I am going to prove one for you. So I want you to see how easy it is. All right? It's just very straightforward to rationalize this with ourselves. So, I'm going to prove this one. Be amazed by my proof skills here. You're just going to be impressed. This is really complicated stuff here. Now I have vectors. I want to show that if I add two vectors together, the order doesn't matter. All right? So, I have two vectors. I want to talk about them, so I'm just going to write them in component form. I'm going to pretend these are two-dimensional vectors. So let V be, I don't know, first component, second component. Let W be written as W1, W2. I just want to be able to talk about the components if I'm going to add them. My goal is to start here, do a bunch of things I'm allowed to do, and end up over here. So I'm going to start with v plus w. But I have a definition for vector addition. I know how to add them. So this would just be v1 plus w1, v2 plus w2. That's true by the definition of vector addition. And we've defined how we're doing addition. I'm just applying that. Now the idea here is that I don't know if vector addition is commutative, but I certainly know that regular addition is commutative. I mean, v1 is just a number, it's 2. And w1 is just a different number, it's 3. If I take 2 plus 3 or 3 plus 2, does it matter? No, I have that rule for real numbers. I don't have it for vectors, but here I certainly have it for real numbers. So v1 plus w1 is just w1 plus v1. This is just w2 plus v2. Right? This is the commutative property of real numbers, and sometimes we write real numbers like that, with a little weird r. But wait a second. If I use the definition of vector addition backwards, this is just w plus v. By the definition, the strict definition of vector addition. That's what I wanted. Hooray, there's the proof. Okay. These proofs are not hard. They're just saying, hey, we can already do all this stuff with real numbers, and we know how to define addition and multiplication, all these things with real numbers. So just go to the real numbers, do the operation, and kick it back. That's it. But it's also a nice first proof concept here. I can only use the things that I know. I know the definition of vector addition. It's one of the few things I know about vectors at this point. And I know my properties of real numbers. It's like the only tools in my toolbox right now. Okay. Any questions about that proof? Once again, you won't be required that proof on an exam or a quiz. Hopefully you can see that they're not too crazy. All right. So next thing we want to touch on is applications. A couple applications here. Once again, it's not going to be a main focus, but you should know how to do word problems. Word problems can get pretty complicated if we really focus on them. So we're just going to think about the basic ones. Now, these are just some really general steps to working with vector word problems. An important first step that's kind of skipped a lot is identifying which things you're dealing with. Now you have a word problem where some things are vectors and some things are scalars. And there's also variables in there. So you really should go through and ask yourself, this thing that I'm dealing with, is it a vector? Does it have multiple components? Does it have a direction and a magnitude? Or is it just a scalar? A scalar is just a number. After that, we're going to use some sort of relationship to form an equation with our vectors. And then we're going to use our vector properties, those properties, to do the algebra to solve the equation, essentially. And that's basically the process. Now what I'm going to show you here is 4 classic problems. These are 4 classic vector problems, but they're really all the same problem. It's really just one problem kind of in disguise with different words. They're basically all the first one. They're all resultant force problems. One of the things we use vectors for in physics and a lot of different applications is to model force, because force has a direction and a magnitude. And the idea is if I have multiple forces, if I have my chair here and I apply a force to it, it travels in that direction. If I apply a force like this and somebody else applies a force like this, where is the chair going to go? That way, kind of somewhere in the middle. Well, that makes sense. If I have an object and I have a force and I have another force, these are 2 forces acting on this thing, it's going to actually travel somewhere this direction. Somewhere that kind of looks like the diagonal of a parallelogram. Okay. So the actual motion traveled will be the sum of the forces. So the resultant force is the sum of the forces. And if we apply multiple forces to an object, that's the direction it's going to travel. So we do problems like flying into the wind. We have a plane. That is one sweet plane. right? And it's flying. Its engines are applying a force that's causing it to travel in this direction. But there's a crosswind. The wind is blowing, right? And it's forcing the plane that direction. It's pushing the plane in that direction. It's applying a force. Probably much smaller, hopefully, than the force of the engine, but it's applying a force. And where will the plane actually travel? Well, in the direction of the sum of those two forces. It might be steering this direction, but it's traveling in this direction. Right? The sum of those two forces. So once again, this is just a resultant force problem. We're just defining our forces essentially in different ways. A boat against a current. The boat's trying to go this direction, the current's going this direction. Force, force. Where is the boat going to travel? Sum of the forces. And then force diagrams from physics. That's essentially just adding up all these forces. Right, so how many people had physics already? Done force diagrams? Good stuff, right? You just have an object, force here, force there, whatever. What's actually going to happen to this object? Sum of the forces. We add them all up vector style to find the result. All right. So most of the time, the problem with these applications is the terminology. So you'll hear things like this: the force or the velocity relative to the ground, relative to the riverbed, relative to the air, relative to the water, all this kind of stuff. And this tends to be the most complicated piece. Once again, we're not going to focus on these application problems. So if I give you a problem, it's going to be force 1, force 2, find force 3, right? Or find the force that causes it to be still. Something of forces, we're going to avoid this terminology. So the best way to kind of go through one is just to go through one. So let's just kind of model one of these problems. So an airplane is flying at an airspeed of 600 kilometers per hour in a crosswind that is blowing from the northeast at a speed of 50 kilometers per hour. In what direction should the plane head to end up going due east? Alright, so this is kind of a typical airplane problem. And if it's a typical airplane problem, or a boat problem, or resultant force problem, or any of these problems, the trick is really to draw a little picture and draw our vectors. So we're going to start with a little picture here. Our plane is going to be in the middle. We want to find out what's going on here. So the easiest thing to identify right away is the crosswind. There's going to be a force from the wind. It's a crosswind that is blowing from the northeast. So I'm going to call this north, south, east, and west. This is the wind blowing from the northeast to the southwest. If it's acting on my plane, the force should be going like this. So that would be the vector representing the wind here. I'll call it W for wind. Now there's a lot of little subtleties here, right? I'm drawing it assuming that it's blowing exactly from the northeast, like 45 degrees to the northeast. So this was a more realistic problem. They would give you some sort of angle measure or a bearing measure. So I have that, so I know that this angle, for instance, would be 45. I'm going to need that. I also know the length of this vector. What's the length of this vector? 50. Now why is that? Well, what I'm getting here is essentially a velocity vector. It's giving me a direction and a speed to go with it. And so the magnitude of velocity is just the speed. Magnitude of velocity, magnitude of a vector is giving me the length of the vector here. So the speed is going to be the magnitude of this vector. So it has a length of 50. I know the angle there is 45. I know everything there is to know about this wind vector. If I want to throw it into components, I certainly can do that now that I've gotten my direction and my magnitude. This has a length of 50. Now what about the plane? Well, it says the plane is flying at an airspeed of 60 kilometers per hour. So what is airspeed? Gotta be careful here, so the terminology. There is the velocity with respect to the wind and the velocity with respect to the ground. Velocity with respect to the ground says I'm on the ground and I'm looking at this plane. And there it goes. There is the vector that is traveling along. Okay? I can't see the pilot from the ground. I can't see which way he's steering. All I can see is the final version, the final thing this thing's actually traveling in. This accounts for the force of the wind. Now airspeed, that's going to be with respect to the pilot up here. He's steering a certain direction and he's got a certain velocity going up, but that might not be the actual speed that he is traveling. Okay, so when they say airspeed, they mean the speed that his speedometer is reading, not necessarily how fast he's actually traveling. So this would be a component of the velocity with respect to the air, not with respect to the ground. Once again, it's the terminology that's annoyingly confusing here. Okay. But it basically tells me that he is. This is like the force of the engines of the plane vector. And we know how long it is, but we don't really know what direction it is. But we know he wants to fly due east. He wants to fly in this direction. And whatever this force is from the plane, I'll call this the flying vector. I'll call it the steering vector. Steering vector. So wherever he's steering, plus the force of the wind, they better end up getting me going due east. So that's where he actually wants to travel. So I'll call this the flying vector. Okay. Now all I know about that steering vector is that it has a magnitude of 600. So I know some pieces of the vectors. And the last thing is the equation that binds everything together here. What's the vector equation that I can get from this setup here? What's the relationship between these three vectors? Absolutely. S plus W equals F. That's the vector equation. Force from my engines, the plane, that vector, plus the vector that's representing the wind. When everything's said and done, it's going to result in where I'm actually traveling, F. So I have that thing going for me. So what I'm going to do is I'm going to call this theta. It's the piece that I don't know that I'm really trying to find. If I knew theta, I would know everything. So all I have to do is break these things into components. So I know the components to S. S is going to equal 50 times the cosine of 45, and that's going to be a negative value. The y component is going to be negative 50 sine of 45. I'm sorry, that's W. Thank you. Thank you. S is going to be, well, I know the magnitude is 600, so I'll have 600. I know it's positive in this quadrant. It's going to be cosine of theta, and then 600 sine of theta. And what do I know about F? I do know one thing about F. The y value is 0. He wants to go due east. That's a y component of 0. I don't know this other piece. But because I know how to add vectors, I add them component-wise. I know that the y component should add up. I know that negative 50 sine of 45 plus 600 sine of theta should equal 0. And that should let me solve for theta. Since theta is the only thing I'm missing here. Alright, so this is kind of an example on the more complicated side. This is more the real application here. But the core pieces are, we have vectors that are represented in terms of magnitudes and angles. We had to resolve these things into components, and then we had to set up a little vector equation. So once again, this is much for the exam. So we wouldn't have something so much like this. It'd be force 1, force 2, find force 3, or find the needed force 3. It would get rid of the terminology, which is the frustrating piece. But we do know how to set up these basic application problems, once again, without the terminology. So we'll start class with another practice on that. Now, for tomorrow, we've kind of talked about a whole bunch of ways we can add vectors, subtract them, and we can multiply them by numbers. But how do we multiply vectors by vectors? Turns out there's two ways we can do that. We can take a cross product or a dot product. We're talking about both of those in 12.3 and 12.4. So for tomorrow, begin your 12.1 homework. So that would be due tomorrow night. Read section 12.3. Watch the dot product video on the Mathkids website. And then bring exam 2 questions. So go through the solution key, prepare for 12.3, and that should be everything. All right, and office hours are right now.
Giving you